Good morning, Advanced Chemistry. Today we're going to pick up on 3.6 Notes Part 2, where we're going to start to use solution equilibrium to describe a new factor called KSP based on our conversation from last week on Friday. So just to catch up a little bit, we were talking about saturated solutions and how saturated solutions have the most amount of solute possible dissolved in them. And we said any more than that, and we would see a precipitate formed, any less than that, and we would know we can actually dissolve more solute in that solution. So we were starting to talk about that, and you guys had those solubility curves, and the line on those solubility curves represented a saturated solution. We stopped at this slide here, and so this is where we're going to pick up. It says KSP, so K sub SP. It's a lot like KEQ, except for it has different letters down there at the bottom. So it says KSP represents the maximum number of ions that a solution can hold when the solution is completely saturated or at equilibrium. Remember, we said the only time that a solution can be considered at equilibrium is when it is saturated. So first, while you guys are writing this, I am also going to circle this KSP guy right here and tell you that that stands for, oftentimes it's written kind of like KEQ is with your big K and your subscript SP. That's called the solubility product constant. Solubility product constant is the name for KSP. So you see the SP for solubility product. And that is going to be the maximum number of ions that a solution can hold when the solution is completely saturated or at equilibrium. So I have an example here of calcium chloride, and this is calcium chloride that's going to be dissolving in water. And when calcium chloride dissociates, it will make calcium plus 2 as an aqueous ion and 2 chlorides, so 2 Cl minus 1s that are both aqueous. Now, if I were to ask you to set up the KEQ equation for this, I hope that you would say KEQ is equal to the concentration of Ca plus 2 times the concentration of Cl minus 1, and that would be squared because in the balanced chemical equation we have a coefficient there of 2. And then we would not put CaCl2 on the bottom because it's a solid and its concentration is constant. Well, it turns out that if this is a saturated solution at equilibrium, all we do is we just change that to be more specific. So it's just a more specific type of KEQ. It is specific to a solution that is saturated. So when equilibrium exists, remember if we were to add in more solid, that would just come out as a precipitate because the solution could not hold any more ions. So this is the maximum concentration of ions in a saturated solution. Any more ions than that you try to put in, and you're going to get a precipitate. So KSP can be thought of as that line on your solubility curve as well. So when you set up a KSP expression, let's look at what we did. First, we wrote out the dissociation. So we took CaCl2 and we wrote how it was dissociated. Okay? And then we took and we wrote the KEQ like normal, but it's just more specific. Every single time that you write this dissociation, you're not going to have a denominator because that denominator is going to be something that is not aqueous. So KSPs only have a numerator. This means that the larger KEQ is, so I'm going to say therefore, whoops, did not mean to do that. Therefore, the bigger, so I'm actually jumping ahead a little bit. Therefore, the bigger the KSP, the more soluble the compound is. So a bigger KSP means that solution can hold a greater concentration of ions. The more concentration of ions you have means the more it's dissociated, which means the more soluble it is. Going back up to the top, KSP is equal to the product of the concentrations of each ion in a saturated solution, and then that's at a specific temperature because KSP is highly dependent on temperature. So depending on what your temperature is, that KSP value is going to fluctuate quite a bit, as you can see from your solubility curves. What I hope you can also see from your solubility curves is that some things are much more greatly affected by temperature than others. So you have some where those lines are very steep and sharp, such as potassium nitrate, and then some that are pretty flat, so they aren't really affected all that much by temperature. So let's apply our idea of KSP now to some situations. So the first thing I'm going to have you guys do today is find KSP from solubility. So in other words, when you look on your sheet and I tell you at 50 degrees, what is the KSP of potassium nitrate? You should be able to do that. So solubility is given in grams per 100 grams of water. This should really say of solution for our purposes. So solubility is given in grams per 100 grams of solution. Now, in some cases, like it may actually say water, but we're going to need to assume that's 100 grams of the solution so we can apply it to molarity. Here are your steps to take when you're doing this. So when you're finding KSP from solubility, so you start with solubility and we're going to find KSP. Number one, you want to find the molarity of the compound. Now, hopefully at this point that's really easy for you. So that's from your solubility. So find the molarity of your compound based on your solubility. Number two, you're going to use a mole ratio to find the molarity of each ion. And then you're going to plug the molarity of your ions into the KSP expression and solve. So it's a pretty easy three-step process. We're going to go through one together, and you guys are going to do some examples. I'm going to even tell you which ones are like this. So at this point, if you need to pause to get the rest of these steps written down, go ahead and do that, because we're going to move on to the next, to the example problem here. So in this example problem, it says, what is the KSP value of silver chromate, at 25 degrees Celsius if the solubility at the same temperature is 0.0035 grams per 100 grams of water? And actually we should change this to say per 100 grams of solution. So if you look at the steps there, the first thing that we want to do is we want to take solubility in grams per 100 grams and we want to change it to moles per liter. I would actually argue that before that, going back to the previous slide, you may want to just add in there that what you'll want to do somewhere in here before number 3, and I would just go ahead and do it to start with, maybe right here, is to write your dissociation and your KSP expression. So let's start with that. Write your dissociation and KSP expression before we go on doing other things. So if I know that what we're dealing with is silver chromate, and remember, this 25 degrees Celsius is just kind of extra information. So we know that it's going to be specific for this temperature. Oh, I spelled degrees wrong too. It's going to be specific to this temperature, but it may be different at a different temperature. It has no bearing on our actual calculation right now. So let's start with silver chromate. Got to write that correctly first. So silver chromate, we have silver plus 1, and chromate is CrO4 minus 2. So when I write that compound's formula, I'm going to have 2 silvers and just 1 chromate. So go ahead and clean this up a little bit. So I have Ag2CrO4 as a solid, and then when that solution is saturated, I'm going to have 2 silver ions that are aqueous and 1 chromate ion that is aqueous. And so therefore my KSP is going to be silver, and its concentration is going to be squared, and chromate not squared. So there's my KSP. So in other words, in order to calculate KSP, which this is asking me to do, what is KSP? I'm going to need to know the concentration of silver ions, and I'm going to need to know the concentration of chromate ions when the solution is saturated. And that is all based on this number right here, because that is where it is saturated. It's just not in the same units as we want down here. Down here we want them in moles per liter, and right now we're given grams per 100 grams. So we're going to go on and we're going to find the molarity of this compound in moles per liter. So to do that, I'm going to clean this up a little bit. We are going to take, whoops, I'm jumping ahead again. We are going to start with 0.0035 grams of silver chromate per 100 grams of solution. And we're just going to change up our units. And you guys should be pretty comfortable with this by now. So first what I'm going to do, and it doesn't matter what order you do this in, but I'm going to take my grams of silver chromate and change that to moles. And I'll help you guys out here. The molar mass of silver chromate is 331.73 grams per mole. So that's going to give me moles per 100 grams. And then I'm going to say there is 1,000 grams of water or solution in 1 liter. I'm going to assume that the density is 1. And when I do that, I'm going to get a concentration of the whole compound as, this is what I'm getting in my calculator, 1.06 times 10 to the negative 4th, and that's in moles per liter. Now to set up a mole ratio here, if I go back to kind of my overall dimensional analysis setup here, if I have 1.06, whoops, I'm really struggling with this today. If I have 1.06 times 10 to the negative 4 moles per liter of the whole compound, whoops, Ag2CrO4, then with a simple mole ratio from my first little from my dissociation equation there, I know for every 1 mole of the whole compound, I'm going to have 2 moles of silver ions, right? Based on that balanced chemical equation, my dissociation equation. So for every 1 mole of the whole compound, I'm actually going to have 2. So for my silver ions, I'm going to have 2.12 times 10 to the negative 4 moles per liter. So remember, that was one of the things that I needed. So for KSP, I'm going to write it up here. Remember, for my silver, I needed that first, 2.12 times 10 to the negative 4. Now I know that concentration, and that's going to be squared. For the chromate part, I'm just going to erase this here. For my chromate part, that is a 1-to-1 ratio. So that's even easier. So for every 1 mole of that whole thing, Ag2CrO4, I'm going to have 1 mole of CrO4 negative 2. It's a 1-to-1 in that balanced chemical equation. So that's going to come also out to 1.6 times 10 to the negative 4 moles per liter. So I can go ahead and plug that in up here, 1.06 times 10 to the negative 4. So to solve for KSP, I'm going to multiply 2.12 times 10 to the negative 4 squared by 1.06 times 10 to the negative 4th. And when I do that, the answer comes out to be 4.76 times 10 to the negative 12th. And again, just like KEQ, because the units for KSP can vary, units are generally left off. So we followed the steps. We wrote out our dissociation equation and KSP expression. We changed our solubility to moles per liter. We found the concentration of each ion based on that using mole ratios, and then we plugged it in. Just so you guys know, these questions on your practice problems, or the one that we just did, are like problems 3, 4, 5, and 8. Those ones are all exactly the same. What if you were asked to go backwards now? What if you were given not the solubility, but the KSP? So here are your steps for that. So finding solubility from KSP. So in other words, now you know KSP, and you're going to try to find solubility. So first thing again, I actually wrote it in this time, is set up KSP expression and do that from your dissociation equation. Then this is the hardest part right here, number 2. Use mole ratios to substitute X's for ions. I'll show you how to do that. Solve for X. Your units are going to be in moles per liter, and then to convert to whatever units are necessary. So again, I'll have you go ahead and pause that so you can write it down. But these are your basic 4 steps, and we'll do an example. Okay, so here's our example. It says the KSP of barium fluoride is 1.84 times 10 to the negative 7th. And again, it's specifying the temperature, but it doesn't factor into our calculations. Just know that it will be different if it's at a different temperature. What is the solubility in grams per 100 grams of solution at the same temperature? Now, when it says what is the solubility, it means of the compound. So that becomes really important because your compound solubility is not going to be the same as your solubility of an individual ion necessarily. So let's take a look at what's going on here. First step is to set up your KSP. We do that from your dissociation equation. So we have BaF2, which is going to dissociate into Ba plus 2 and 2F minus 1s, and those will both be aqueous. So our KSP, step 1, your KSP is going to be equal to the concentration of Ba plus 2 times the concentration of fluoride squared, and we know that that is equal to 1.84 times 10 to the negative 7th. Now, what I want to do is this. I want to know the solubility of that guy right there. So I want to have my X be whatever ion has a 1-to-1 ratio, if I can. So the 1-to-1 ratio is between BaF2 and Ba. So I'm going to substitute Ba with X, because I don't know the concentration of Ba. But I know whatever the concentration of Ba is, it should match the concentration of BaF2 because you have a 1-to-1 ratio. So I'm going to make that X, which means fluorine, if I make 1 Ba plus 2, I'm going to make double the amount of fluorine. So fluorine is going to be 2 times X. It's going to be whatever barium is times 2. And that's going to be squared, and that's still going to be equal to 1.84 times 10 to the negative 7th. Well, if I square 2x, I get 4x squared times x should give me 4x cubed. And that equals 1.84 times 10 to the negative 7th. And yes, I can hear you guys out there right now that doesn't look like a 3, so let me try that again. 4x cubed. Okay, so I need to divide by 4, and actually that is going to give me x cubed is equal to 3.58 times 10 to the negative 3rd. Oh no, I'm sorry, negative 8. Oops, none of that is right. That's the actual answer. X cubed is equal to 4.6 times 10 to the negative 8th. And then you got to find how to take cube root on your calculator. And so x comes out to be 3.58 times 10 to the negative 3rd. And that's in moles per liter. Now that's why we wanted to have our X be our BA, because remember, whatever BA plus 2 is also the concentration of our whole compound, because it's a ratio of 1-to-1. So now we have the what's called the molar solubility, and we just need to change it into grams per 100 grams of solution. So now it's just dimensional analysis at this point. So we've got 3.58 times 10 to the negative 3rd moles per liter. I'm writing really small, sorry. And for every 1 mole of BaF2, BaF2 has a molar mass of 175.34 grams. And so that is going to give us grams per 1 liter, So that comes out to be, let's see, I didn't punch it in yet, 3.58 times 10 to the negative 3 times 175.34 is 0.627 grams per liter. And it said grams per 100 grams. Well, that's just 1/10. And so 100, we want 1/10 of that. So we just want to multiply it by 0.1. And so we'd have 0.06277 grams per 100 grams. Because it's 1/10 of that. So there we go. These are like the rest of your practice problems, and you're going to skip some. I'll put those on the board. But give those a try, and we'll see how it goes, and have a most excellent day. See ya.